Okay, good afternoon, everyone. This is going to be our last lecture for this course. We're going to learn about two things today. One of them are Gaussian mixture models, which the way we're going to use them is like a soft version of k-means that works a little bit better usually. And second, we're going to learn a method a powerful method for maximum likelihood optimization called the expectation maximization algorithm, which we'll use for our GMM fitting. So just to start at the beginning, when we consider multivariate Gaussian distributions, these are just Gaussian distributions where you have a set of random variables that are all jointly Gaussian, the joint probability density function is Gaussian. It looks like this. It has this form. So you have an exponential part where you have a mean vector, you have a covariance matrix Q that gets inverted, and here you have a scale factor where you take the determinant of that matrix and so on. So this is just a multivariable generalization of the scalar Gaussian that we've worked with a lot. And so this is parameterized, like I said, by mean vector covariance matrix Q. If you plot its PDF, would be a 2, where you have like the x vector has 2 scalar components. The PDF looks kind of like this bump. And as you can see in this picture, the bump is kind of stretched out in a particular way. If you plot a scatter plot, so if you generate a whole bunch of realizations of this random variable and you plot a scatter plot, you might get something like this, and you can see again that it's stretched. If you want to know exactly how it's stretched, you look at the eigen decomposition of that covariance matrix, similar to what we talked about last time. It turns out that the eigenvectors are, okay, so number one, the contours of this PDF are ellipses. And number two, the principal axes of these ellipses are given by the eigenvectors in V. And the lengths of those principal axes are given by the square root. There's actually a typo, this should be plus 1/2. A square root of the eigenvalues. So eigenvalues and eigenvectors of Q tells you exactly how that Gaussian PDF is stretched. Okay, so now that's a single Gaussian. Now slightly more complicated is what's called a Gaussian mixture model, where you have a data set that looks like it has maybe several different Gaussians. So here the scatter plot, you see a bunch of values around here that individually look Gaussian, but then you have a bunch of values over here, and that subset looks Gaussian. But really, you actually have both of these things going on. And now that you see this picture, you might understand that this is very similar to the pictures we saw as examples of where you might want to use clustering, where you get a data set like this, and you would like to automatically recognize that these points come from one cluster and these points come from another cluster. So if your data set has this general look, then you might say, oh, this is something that I could apply a Gaussian mixture model to. And once I have that Gaussian mixture model, it's going to give us a way to cluster directly. Okay, so our Gaussian mixture model looks like this. So the probability is a weighted sum of capital K different Gaussians. So here's the sum, here's the weights, gamma K, and here are the individual Gaussians. So now each Gaussian has its own mean and its own covariance. And the weights must be non-negative and they must sum to 1. So, and if that's true, then this P of X is a valid density. Yeah, so of course, like looking at this picture over here, there would be a mean over here from the first Gaussian, and then it has a covariance matrix with those elliptical contours, and we have another mean over here, and this covariance matrix has different contours, different eigenvalues and eigenvectors. So the way that we do clustering with a Gaussian mixture model, step one, we fit the parameters of our model, all these guys here, to our data set. Now, once we have that model, it's going to be relatively easy, we'll see how, but it's going to be relatively easy to determine for a given x, let's say my x is over here, whether this is closer or more probable, or whether this one is closer. And that's how we can do clustering. And in fact, what's a little bit different here than k-means is if I have a point over here, I can actually give you a soft clustering, which is like saying, well, with probability 0.8, I think it's coming from here, but I'm not super confident with probability 0.2, it might actually be coming over here. So whereas k-means would have just said, this point is associated to this cluster, don't ask me any more questions. So this gives you a little bit finer grained information where you can make more informed decisions. So that's sort of a high level overview of Gaussian mixture models. We're going to get into the details of how we do all this stuff, but it's a good time to pause. Are there any questions about Gaussian mixtures or how we're going to use them for clustering? Is it sort of making sense? Okay. No questions at all? All right. So in order to see a little bit more clearly how we're going to use things, we're going to come up with a slightly different perspective on the Gaussian mixture model, which people refer to as hierarchical. And you can perhaps think about it as a two-stage approach to generating a random vector from that distribution. So let's say someone said, okay, I have this distribution with these weights, means, and variances. I want you to generate a bunch of points for this. I want you to generate the scatter plot here. So the easiest way to do that is to break it up into two stages. First stage, you figure out which one of these two components your sample is coming from. Second stage is, if it's coming from this, then you just generate a Gaussian with that mean and variance. On the other hand, if it was coming from here, you generate a Gaussian with that mean and covariance. It's pretty easy to generate samples from Gaussians. So just by breaking it up into these two stages, we take this kind of complicated distribution, we turn the problem into a much easier form. Okay, so again, the two-stage approach would be first draw a component index. So these are the different components. We have components indexed by k. So we're going to call kappa the component index, draw kappa. And so this is a random variable, which mixture is it coming from? And it turns out that this is a discrete random variable, so notice that its values are integers from 1 to capital K. So is it coming from the first, second, all the way to the kth? And the PMF that you use to draw this is just a vector with those different weights gamma. So for example, if I had two components and my weights were 0.8 and 0.2, that means with 80% probability, I would be drawing from the first mixture component with 20% from the second. Okay, so that's what you do in the first stage. And then now that you have figured out which component it's coming from, you just draw x according to that particular PDF. So here we're using kappa down here, the kappa we drew from the first stage. And that's pretty easy. That's just drawing samples from a Gaussian. All right, so is that kind of clear, the way we're splitting this into two parts? Okay, and so mathematically, you could say that first stage you're doing, you're looking at something like this kappa, this new random variable. What is the probability that kappa equals a given k? It is lambda k. And second, what is the probability of x given that kappa equals a particular k? Well, that is this Gaussian PDF where you're using the k you drew from the first part. Okay, so those are the two parts. And if we want to sort of use this back in the definition of px, and just to see that, yeah, this all works out exactly as we're saying. So for any px, if you add another random variable, so you have now joint px comma kappa, if you sum over all the possibilities of kappa, that gives you back px. So we call this the law of total probability. So hopefully you believe in this. Second, anytime you have like p a comma b, you can write this as p a given b times pb. So we're doing that here, but with kappa, with x as a and kappa as b. We're also leveraging the fact that here kappa is discrete, whereas x is continuous, so we have PDF, PMF. And then in the final step, we're just plugging in what is the probability of x given that you know the component is coming from. That's just this Gaussian. And what is the probability you draw the component equal to k? That's just lambda k. Okay, so that's just to try to verify that, yes, the px we gave on the first page is totally consistent with this two-stage approach. Okay, so the main thing that we did here is we came up with a way of introducing a new random variable, an implicit sort of or hidden random variable called kappa. So notice that the original p of x, the way we wrote it originally, you can see there are no kappas. Right? So what we did is we kind of invented this new random variable that was somehow convenient for us. And we sort of came up with a slightly different way of writing our Gaussian mixture that involved kappa. And by doing this, we're making things easier for what we want to do later, because now kappa is really the information we're curious about for clustering. If I give you a point over here, you want to essentially compute what is the probability of kappa given that point x. That will tell you the probability that comes from here versus here. That is exactly what we need to do for clustering. We just need to compute those capital K probabilities, and that is our soft clustering. And then once we know the probabilities, if you really want a hard clustering, you can just pick the index of the largest one. Say, that's my best guess. Okay. So this hierarchical view is super useful. It's not just for this problem, but in a lot of different probability problems. Just kind of a trick to write a probability in a more transparent way. Okay, so that's the hierarchy. Any questions on this? All right. So now let's look at some of the equations. How do we actually compute this key probability? This is what we want to compute. Probability that kappa is some hypothesis k given the sample x that we're trying to cluster. Okay, so what we said from the previous page is we can write px as we did originally, or we can write it in terms of this new hidden variable kappa. Probability that kappa equals k times probability of x given that kappa equals k summed over all the possibilities for kappa. Okay, so this new thing is going to be useful because this actually exposes the quantity we're trying to infer or predict. And we're going to use map estimation. We want to find, maximize the probability of kappa given x. So that's, so for this, yeah, this is just an instance of map estimation, which we saw way back in Unit 4. Okay, so how do we do map estimation? Similar to what we saw before, this is the quantity we need to define or derive. But we don't have a good expression for kappa given x. However, if you swap the order, we know x given kappa, we know probability of kappa, so that's what we can do with Bayes' rule. So Bayes' rule in general says PA given B is PB given A times PA over PB. There's another way you can write this that's sometimes useful, where in the denominator, you write it in terms of the things you already know. So we'll replace PB with PB given A times PA dA. So maybe I'll put a prime on the A to make sure it's not confused with the one in the numerator. Okay, so why is that true? Well, that's true because this is PB comma A prime, the joint probability. And now we're going to integrate out the A part, leaving just PB. Okay, so that's exactly what we've done this first step here. And this second step, that is what we did down here. But down here, our hidden variable is discrete. It's not continuous. So instead of using an integral, we use a sum over, A prime. Now it's kappa prime. Okay, so this thing we're trying to compute, now we can see how it is a function of the parameters of our GMM. So here we have the gamma, mu, and q for the k we're interested in. And in the denominator, we have all the rest of them. Okay. So once you know these values, once you fit the GMM to your data distribution, all your training xi's, you know these values. And for any new test point x, you can just plug that in and immediately compute its soft probability. So now you know, 70% chance I think it came from here, 30% from there, and so on. So that's the soft assignment. And if you don't want probabilities, you actually want to know what is the most probable cluster that came from. That would be the hard assignment. You just take the soft probabilities and you simply find the index over which they're maximized, and you call that kappa hat. That's our estimate of the single map estimate of that kappa. Okay, so this is what we do at inference. So this is relatively straightforward. What is not as straightforward, as we'll see, is actually learning all of these, fitting all these parameters to our data. So we'll spend most of our time on that. But before we go on, are there any questions on the inference part, the actual clustering part, once we've done our fit? Okay. All right, so this is just a summary of GMM-based clustering. So the part we have yet to discuss is how do we do the fitting, but assume we can do that. Second step, we compute this quantity here for every sample I in our data set and every hypothesis cluster K, or cluster hypothesis K. So we know all these terms from our fitting, and we know all the xi's from our data set, and we can compute all these values. Once we know all those values here, we just, for every I, we find the K that maximizes them, and now we know the cluster assignments, the hard cluster assignments for that training sample xi. Okay, so just to summarize the previous pages. Now, new topic. To fit the GMM parameters, we would like to do maximum likelihood. So if we could do that, it would look like this. The optimal parameters are the ones that maximize the likelihood P training samples given theta. As we know, instead of using the raw probability, I can use, or the raw likelihood, I can use the log likelihood. That doesn't change anything, but usually it makes our lives easier. And in this case, what's really tricky is the form of the log likelihood. So as usual, we're going to have a sum over our training samples, and that's because this probability involved a product over the training samples, assuming that each sample was drawn independently and identically from some distribution. But what's tricky is that the log of this Gaussian mixture model is really intractable. We can't simplify it. If we didn't have the sum, then log of a single Gaussian, that's easy, right? That's just because a single Gaussian is just constant times e to the power the quadratic in x. But once you have a sum of Gaussians, the log of that is no longer easy. So this is where we get into trouble. and it becomes difficult to figure out how to do this. If you tried to do this with gradient descent, it just wouldn't work well. So we are going to use a more sophisticated approach called the EM algorithm, which is a famous approach that you can use for many, many tasks. This is just one example of the EM algorithm, which is Gaussian mixture model fitting for this clustering problem. Okay, so, all right, so before we move on, are there any questions, anything so far? Okay, so we got sort of the Gaussian mixture model clustering, and now parameter fitting next, EM. Okay, so EM is a little bit tricky, so let me try to describe it from different perspectives. So the first most important thing is, what is this, or what is it in our case here? It's an iterative approximation to generic maximum likelihood estimation. So you can use this for any kind of maximum likelihood problem, especially tricky ones, maybe ones that involve lots of parameters. Some are discrete, some are continuous. It's not really clear how to, like if you have discrete parameters, how do you can't differentiate with respect to them and so on. So, so it's a pretty sophisticated technique. You can use it for a lot of things. What you can say about it is it's guaranteed to converge to a local maximum of the likelihood, okay? But unfortunately, it can get stuck in a bad local maximum. And so in order to get around that issue, you tend to have to use a good enough initialization with EM. So it's one of these things where if you don't initialize well, you can really do terribly, but if you find a decent initialization, it can be a really powerful method. Okay, so this EM algorithm iterates between two steps. So in this case, T is our iteration index, 0, 1, 2, so on. So and these are the two steps. It looks a little bit strange at first. So there's this conditional expectation of this quantity. And what you do here is you just compute this function called Q. And then in the second step, you maximize that function over theta. Okay, so what are these theta t's? This is your best guess of theta at iteration t. So in the second step, you update your guess, and in the first step, you use your previous guess to compute this Q function. Z are some hidden variables that you, in general, have to be a bit clever how you define them for a given problem. For a given problem, maybe there's different ways to define the hidden variables. Different choices will give you different EM algorithms. Some will work better than others. For our clustering problem, it's going to be pretty clear what our hidden variables are. Those are our kappas. So that's what we're going to use for our hidden variables. But in general, for EM, it's an interesting choice. Okay, so overall, we have these two steps. The first one, people call an expectation step. The second, they call a maximization step. So it's pretty clear why the second one is called a maximization step, because it involves this maximizing over this hypothesis of what the parameters are. But why is the first step called an expectation step? It looks like this kind of crazy, complicated, conditional expectation. Okay, so let's break this down. What exactly is this conditional expectation? So it is what's over here. So if you remember the way that expectation or conditional expectation is defined, there's an integral where you're essentially doing some sort of average over this term that appears here, and you're averaging over, in this case, this random variable, z, but you're conditioning on x, which are just your training data, that's known, and you're conditioning also on your guess from your previous iteration. Okay, so essentially, this expectation manifests as an integral where you're averaging this over this probability distribution here. Okay, so that's sort of how the Q function is built. And now let me give you sort of maybe a simpler case of this. Imagine that this probability was the simplest thing possible, which is a spike where all the probability mass is concentrated on what we'll call z hat. In this case, z hat will be your best guess of the hidden variable at iteration t. Okay. So this quantity acts like our belief or our knowledge about z at iteration t. If I'm absolutely confident that z is this thing, z hat t, no uncertainty at all, I would put all my probability mass at z hat. And what happens in that case if I plug this into this integral? This is a Dirac delta function. This is like this spike that has area 1, but it's like infinitely tall, infinitesimally narrow. You may have seen this in signals and systems or DSP courses, probability courses. So if you plug this spike into here, this whole thing simplifies down to this. So this says it's the log of the joint probability of x and your guess, your best guess of z hat at that iteration. Okay, so that's what it would be if you were absolutely positive in your guess about z hat. Now in reality, when we're at this iteration of the algorithm, we don't exactly know what z hat is. We have a belief, well, it might be this, it's probably more likely than this than that, and so on. And so essentially we have a probability distribution. That is this thing. This is like our state of knowledge about z, given our data and given our guess about theta at that iteration. And so instead of just plugging in z hat into this function, we're just averaging that function over all our beliefs about z hat. We're sort of just taking the average. So that's what this Q function is. So that's a little bit of sort of high level trying to explain a little bit about these. It may not make sense yet, but let me give you another take on it, which is through something called iterative maximization of a lower bound. So I'll start with this picture. So imagine that this here is the likelihood function. And theta is the parameter that I'm trying to maximize. I'm trying to find the theta that maximizes the likelihood. So as you can see with this likelihood, it's not differentiable, right? So the technique we've been using all semester, which is to find where the derivative goes to 0 and then set theta equal to there, that's not going to work here because the derivative doesn't actually go to 0 anywhere. So instead, there's sort of an interesting process where what you can do is, let's say you start with this guess for theta, and so the value of the likelihood at that point would be this dot. So let's make a lower bound on the likelihood function that's friendly to work with. In this case, maybe we made this quadratic lower bound. Because this is a nice lower bound, what I can do is I can easily maximize it. I can easily find the point at which its derivative goes to 0. And so from here you can see that that would be this point. Now I have a better guess of theta than what I started with, and now I'm going to make a new lower bound that's going to be tight at this point. And by tight, I mean my lower bound perfectly matches my likelihood there, but otherwise could be less. So my new lower bound, the next iteration, is going to look like maybe another one of these parabolas, like this. That is tight right there. Now we repeat the process. Because this is a nice friendly lower bound, I can maximize it, and the maximum is now going to be here, and that allows me, now I have a better guess, now I can do another tight lower bound. I'll do it in green. Maybe it looks like this, and so on. And you can see this is getting closer and closer and closer to the peak, which is really where I want to be, right? That's where the peak. So this is a nice approach to optimization in general. It's actually used in many other applications, but this is also what explains this EM algorithm. So with this intuition, I'll be able to show you where exactly all those equations are actually coming from. Right, so are there any questions about this idea? Is this making sense? Okay. So let's see how this manifests to become the EM algorithm. So let's start with a generic likelihood function. Any likelihood you want. X is our data. Theta are our parameters. Or this is actually the log likelihood. So Now let's take a belief about some hidden variable z. And I'm going to call that belief p hat z. And this can be anything. It's any valid PDF on z. Doesn't matter what it is. So hopefully you agree that this equals this, because notice that here I'm integrating over z, but this likelihood term has nothing to do with z, right? So I could pull this out of the integral, after which what remains in the integral is just a PDF p hat integrated over its argument, which must integrate to 1, no matter what, right, for any valid PDF. Okay, so hopefully you agree in this equality. Is everybody good with that? Okay, so now we're going to write this term here, or actually this term here, in an incredibly complicated way. So number one, we're going to sneak in a p hat in the numerator and denominator, which obviously cancel if you like, but we're going to put them in there for a reason. And then we're going to write p of x in sort of a complicated way, which is this ratio. Okay, so why does that hold? So I can write p of x as p of x times p of x given z divided by p of z given x, like that, right? P of x equals this, because I'm just multiplying by 1. But now that I've done this, you might notice that the numerator can be written as this joint probability pz and x over pz given x. So it's a weird thing, but it's true. And that's exactly how we turn p of x into that ratio. Okay, so now we have this sort of strange, complicated way of writing p of x, where we've now kind of snuck in our hidden variable. Now it's kind of merged with the x's in these cases. And the last step is to break this log thing into 3 terms. So as we know, the log of a over b times c can be written as the log of a minus the log of b plus the log of c, right? And so for a, I'm using this. So we have log of a. For b, I'm using this. So we have minus log of b. And then for c, I'm using this. Okay. And now it turns out that we start to see some recognizable things. So the first thing we're seeing is that strange term that was the Q function in our likelihood, but we'll get into that more later. The second thing, if you've taken a course in information theory, or maybe you've seen this even otherwise, is called the entropy of this distribution p hat z. It's the integral of p hat times log p hat, basically. It's sort of a measure of how much uncertainty there is in the random variable defined by p hat. And the third term is, again, a term that is studied quite a bit in information theory, called the Kullback-Leibler divergence. It's a way to measure the discrepancy between 2 different PDFs. In this case, the PDFs are p hat z and this one. Okay, so when those PDFs are identical, look at what happens. If these are identical, the ratio is 1. Log of 1 is 0, right? And if this term is 0, then this whole thing goes away. So when these distributions are equal, this term is 0. But anytime they're not equal, this term will be positive. So that's kind of the key point. And so now we have this sort of, we're writing our log likelihood in terms of these 3 different terms. And what's interesting about this is that if I remove this positive thing from my log likelihood, or positive or 0, the value gets smaller, right? If I remove something positive, it gets smaller. In the worst case, this is 0, and I don't remove anything, and it stays the same. So by removing this, I get a lower bound, which is this new thing that is less than or equal to my log likelihood. Okay, so that's what we have here. The log likelihood is less than or equal to the first term plus the second term. this plus the entropy. Okay. So that is this log likelihood. That's how we can create this here. And the interesting thing is this becomes an equality when the KL term is 0. So when p hat equals p, you get an exact agreement. Okay, so it's a tight lower bound, and essentially that's kind of, this is sort of an illustration of the way the EM algorithm works. So in the E step, what you do is you take this lower bound and you tighten it by choosing p hat. In particular, you choose p hat, your belief on z, equal to this, and then all of a sudden your lower bound is perfectly tight, at least at the parameter theta that you're at. Because notice this depends on theta. So that's where we get this tightness at the point theta. In the next step, you take that lower bound and you maximize it over theta. And that's where we get, that's how we find this theta. And then you repeat. Okay. So this is how this is actually, this idea is manifesting in our EM algorithm. And now that you can see, now you can start to see where that strange function that we saw came from. Okay, so just to explain this with a few more equations. So the bound tightening goes like this. So this is our log likelihood, exact equality of our lower bound plus this non-negative KL term. To tighten the bound, I want this to be 0. To make that 0, I set my belief, p hat, to this pz given x parameterized by theta at iteration t. And this is exactly what EM uses at iteration t. So it's exactly this conditioning that we saw. The other step is the maximization. The maximization of the lower bound is, so this is the lower bound. You want to maximize this over theta. Well, you can forget about this because this doesn't depend on theta. So just maximize this alone. And that is exactly what we have here. Just maximizing that first term over theta alone. Okay, so that's an explanation now, or derivation of where this EM algorithm comes from. Like I said, you can use this for any likelihood you want. You just need to come up with a nice choice of hidden variables, and then you apply this, and if you have a good choice of hidden variables, this thing will converge very quickly and give you a very good approximation to the maximum likelihood solution. If your likelihood is concave, you will go to the true solution. You'll converge there. If it has multiple local maxima and you initialize well, you'll also get the true ML solution. Okay, so that's the EM algorithm. What we'll do next is we'll apply it to GMM fitting. But before we go there, I just want to pause here. Any questions on this? I know that it's a lot, but this is super useful if you're doing research in fields related to machine learning. Often with my grad students, it comes up, and I said, remember we talked about this at the end of this course? And they go, oh yeah, and they go back to these slides, and they look through them and relearn it. So, okay, it's a very powerful, very useful approach. Okay, so now that we have the approach, the last step is to apply this approach, EM, to our GMM fitting problem. So we have to choose our hidden variables z, and we're going to choose these kappas. If you remember, the kappas were, kappa I is the unknown cluster index from 1 to k that sample xi comes from. So these are, we don't know what they are. We're trying to figure them out. If I knew these, I would have a perfect clustering. Okay, so remember that the EM algorithm uses this Q function that looks like this. When we saw it previously there was a z. There was z's instead of kappa, but now I'm just setting z to kappa. So that's why we see kappa now. All right, so let's go through this. So as always, when we have n different data samples, we assume that they're independently drawn IID. So this turns into the product of the individual xi's with their own individual kappa i's here. You take the log of the product, that gives you the sum of the logs of this. We can move the sum out. In doing so, this multi-dimensional integral that was integrating over all the different kappas turns now into a single dimension integral that's nice and tractable because there's only one kappa that's left in here. All the other ones got integrated out. Okay, now you might say, well, this is kind of weird. We have discrete random variables, so why are you doing this with an integral and with a PDF instead of a PMF? So let's replace that PDF, that integral with a sum, the PDF with a PMF. We have this. And so now we have probability of kappa equaling k given data sample xi and given our guess about the parameters. Let's give this thing this name. So this is, again, you're saying what's the probability that the ith sample comes from mixture component k given my knowledge or my guess at iteration t. That's what this thing is. It's going to come up over and over again. Well, it turns out we already derived this. This was actually something we derived back here. So here it is. So we're just going to plug this expression in. Plug that expression in right here. So that's it. Now over here we have this joint distribution x comma kappa, and we can split this into x given kappa and probability kappa. So if you remember x given kappa, that's easy. That's just a Gaussian. And the probability of kappa equals k, that's easy. That's just gamma k. Okay, so we basically, the Q function turns into all these things we know. We have gammas, we have Gaussians, we have certain parameters that depend on our guess at iteration t. Those are the ones labeled with the superscript t. But then we have other parameters, these guys, that are actually free variables. These are the things we need to maximize over. So those will be the things in the M step that we try to maximize. Okay, so this is our Q. This is our E step. Any questions there? All right, so let's now look at the M step. The M step, we try to maximize our Q over our free variables theta. Let's plug in the Q from the previous page. So we have, you can see there's a term with some known variables and then an unknown variable we're maximizing over. Known variables, unknown things we're maximizing over. It's a little bit more complicated because these gamma k's are not totally free. They must sum to 1. Also, they must be non-negative. It turns out that we won't need to explicitly enforce the non-negativity. It will happen naturally, but we do need to explicitly force the summing to 1. So the way we do this, we learned a little bit few units ago about Lagrange optimization. If you have an equality constraint, what you do is you take the thing you'd like to maximize over, and then you add Lagrange variable times that equality constraint reformulated to equal 0. And now you do your optimization over the thing we're originally optimizing over, which is gamma, as well as lambda. Okay, so the first thing we'll do, and now we have an unconstrained problem, so we can set the derivative with respect to lambda k to 0. So this is the thing this is our new cost function. And this is pretty straightforward. If I want to take the derivative of this, okay, so notice, first of all, there's many k primes. There's a single k here. So out of all the k primes, there's only one that matters. It's k. So that means that the sum over k prime vanishes, but the sum over I is still there. When we take the derivative of this just turns into 1 over gamma k. and then what remains is this sum. Then over here, take the derivative with respect to gamma k again. All but one term in the sum disappears, and it's just going to give us a derivative of 1 times lambda, which is this. Okay, so we can rearrange this by multiplying both sides of that times gamma k, and we get this relationship here. Now we know this holds for all indices k, so that means it must also hold if I sum over all indices k. So summing over k, get this term and this term, but now we can use this trick where we know that the sum over the gamma k's must be 1. So basically we can just replace this with 1. Furthermore, due to the form of those other guys, they also sum to 1 over k. So that means this whole thing turns into 1. Now we can see exactly what lambda is. Lambda must equal n. Now that I know what lambda is, I can essentially plug it into here, and I can figure out the rest of the variables. Okay, so let's see exactly how we do that. So, so coming back to here, let's say we want to solve for gamma k. You can see that gamma k must equal this. Now we know what lambda is, it's n, so we plug that in. And we know all these variables, so we can find exactly our maximum likelihood estimate of gamma k, or just maybe local maximum likelihood estimate. And that is what we will assign to the maximum we use in the next iteration. Okay, so that's maximizing over gamma k. The other ones are a bit easier. We have to maximize over the mu k's also. So we just set the gradient with respect to this, with respect to mu k of this to 0. And we've seen this stuff before. The gradient of a Gaussian, we get this nice quadratic plus a constant. Now we take the gradient of this with respect to mu k, and we get this thing here. And we can bring the q out to the front, and we know that 0 equals q times this. Now, this is a invertible matrix, so the only way to make the output of that 0 is to actually make this itself 0. And if we want to make this 0 by choosing mu k, it's easy to do so. We just put this in the denominator of that, and we get our expression for mu k. So these are all known quantities. So now we have an estimate for mu k we can use in the next iteration. And it turns out the optimizing for qk is similar, so I'm not going to get into the details, but basically, this is the summary of the algorithm. We repeat this at each iteration. So using the previous iteration guesses, we first compute our gammas for all k and I at that iteration. Then using those gammas, we can find these guys, mu's and q's, and we repeat. We just iterate this over and over again. Right, so that's essentially how we use EM for GMM. A couple more details. We need to initialize it well, so it's common to use k-means plus clustering. So you do k-means, that gives you a hard clustering, and you set your initial gamma k's to the fraction of samples that k-means assign to cluster k. And you can set your mu's and q's to the mean and covariance of the samples that k-means plus assigned to k. So just empirical means and covariances. And one last note is that when the dimensions start to become large, you have to estimate a very large covariance matrix here, so it's common to not try to estimate the entire thing. You just pretend it's diagonal, and you just estimate the elements on the diagonal. It's a pretty common trick to reduce complexity. Okay, so that's EM for GMM. I'll just show you a visual example. So here's our original data set. For our initialization, rather than, like in k-means, we just initialize with 2 centroids, which are just 2 like points. Now we have to initialize with essentially Gaussians. So we have to come up with some means and some covariance matrices, as well as some weights. And so we're going to use a Gaussian with contours like this. So one of the means is here, one of the means is here, and you can see these are identity covariances, which give us round contours. So the first step, what we do, is we do the soft clustering of all these green points. So the way the colors work here, if a point is purely blue, then it's purely assigned to here. If it's purely red, it's assigned to here. But if it's purple, that means you don't quite know whether it's assigned here or here. So these are like probabilities again. It's just now the probabilities are shown red versus blue from 0 to 1. So that's the soft assignments. You can see that it's pretty clear that some of these are coming from blue, some from red, but the points in between, the algorithm is acknowledging it doesn't quite know how to assign them. Anyway, once you have those soft assignments, you essentially compute like a weighted, a blue-weighted conditional mean, or blue-weighted empirical mean, and that puts you here. A red-weighted empirical mean puts you here. You can compute this blue-weighted covariance matrix and red-weighted covariance matrix, and that gives you those contours like that. And now that you have these new Gaussians, you repeat the process again, where you again generate soft probability estimates, and gradually these contours sort of rearrange themselves until you get a pretty nice clustering where, k-means would have just told you there's a centroid here, there's a centroid here. GMM tells you more than that. It tells you there's a mean here and a mean there, but it also tells you that this cluster has a certain shape. It's stretched in a certain way, it has a certain extent. This one is bigger, it's stretched in a different way, and so on. So that's how this is differing from k-means. All right, so any questions on EM? All right, just a couple more slides. So if you want to compare EM, GMM, and k-means, EM computes these soft assignments, k-means only hard ones. EM estimates covariance matrices. K-means kind of implicitly uses identity covariance matrices with a very small epsilon. That essentially means that EM uses piecewise curved boundaries, where k-means its Voronoi cells use piecewise linear boundaries. EM essentially tries to estimate these probability weights, where k-means sort of implicitly assumes that they're all equal. EM is more computationally expensive than k-means. Both can get stuck in local minima, both benefit from a good initialization, and both are implemented in sklearn. Okay, so we're almost done. Let me just show you a kind of interesting application of this to color quantization. So when you look at typical images, red, green, blue color images, you use 8 bits for the red pixels, 8 for blue, or 8 bits for red, green, and blue for the intensity. And so that means that you have, for each red, green, and blue, you have 2 to the power 8 possibilities, 256 possibilities of brightness. Now, if you count up the total number of bits you're using for those 3 channels, it's obviously 24. So you have a total of 24 bits per pixel. And if you then ask the question, how many different colors can you represent? It's a huge number, 2 to the power 24, almost 17 million unique colors that you can describe with an 8-bit or standard true color image. So our goal is to do some sort of compression, where rather than using 16 or 17 million possible colors, we're going to squeeze it down to 16. And so that means we're going to be able to represent our image with 8 bits per pixel instead of 24. And of course, this is going to degrade the image, but the key question for us now is, what are the 16 best colors that we can use? So interestingly enough, we can actually treat this as a clustering problem. So maybe if I would try to visualize it, we have our features are in 3 dimensions, RGB. These are sort of real numbers in 3 dimensions. You can imagine that each one of these is a pixel in the image. I have a bunch of, a whole bunch of pixels in this image. Gives me this 3-dimensional scatter plot. And the thing is, I want to find 16 different points which are the best approximation to all those scattered points. So it's like I want to put 1 point here, 1 centroid here, 1 centroid here. Right, so that I want to do that with 16 centroids, and so now all these points over here will be sort of quantized to this, all those points will be quantized to this, all those quantized to this, and so on. So the key question is, well, how do I choose those 16 colors? So now you can see it's a clustering problem. So the way we're going to do this, just to save computation, is this picture has like 273,000 pixels. So instead of using all of those, we'll just take 100 or 1,000 pixels at random. We'll do our fitting on the 1,000 pixels, and then once we know our fitting or our clustering, we can apply the quantization to all the rest of the pixels. So we can compare k-means and EM-GMM, and let's take a look. First, let's look at the original image. We don't have 16 million different pixels, so we can't get 16 million colors. In total, we have 96,000 unique colors in this image. If you look at things like the horizon, you can see that there's a very gradual change in the color from blue to pink and so on. You can also see that there's an island here, there's a bridge here, and so on. When you do Gaussian mixture modeling, now there's only 16 different colors in this image. And so you can see what happened to the sky. This nice smooth gradient turned into basically like 3 different sky colors. The horizon here, now there's these sort of stripes. The island, you can still see it. You can still see the bridge and so on. That's Gaussian mixture modeling. If you do k-means, now you can see things are not quite as good. The island here just kind of gets washed out and combined with the background and so on. So a lot of the boats are disappearing. So that's sort of what you expect. GMM is a more complicated, more careful procedure. K-means is sort of like a rougher approximation. So the results with GMM are a little bit better. Okay, any questions on this? All right, so let me just race to the end then. We talked a little bit about model order selection before. Basically, the question is, in practice, if you don't know how many components to cluster into, you have to figure this out somehow, and there's a bunch of techniques to do this. If you're interested, you can click on the links here. Another question is, what features should we use to do clustering? Should we use the raw features, or should we be clever, like the SVM, and actually use some sort of kernel-based features? And yes, you can use kernel-based features, and that is called spectral clustering. And so someone asked me in the last lecture, like, how well would k-means work on this half-moons data set? So this is a nice picture from scikit-learn documentation. It shows a whole bunch of different algorithms. So here's mini-batch k-means and a bunch of other algorithms. So Gaussian mixture modeling is on the right, and a whole bunch of ones in between. And you can see that all these different algorithms behave differently. So as expected, k-means or GMM, they simply don't work for that 2 moons. Neither do they work for these rings. But there's more sophisticated, like spectral clustering, works great in both those cases. So using kernel features is better than the raw features. Once you look at data sets like this, now you can see Gaussian mixture models excel, because it's exactly what they're set out to do, whereas k-means has more trouble. It's not good because the clusters have, or these little things have different sizes. Some of the other, like spectral clustering, also does great. Some of these other techniques simply, they fail to cluster this into 2 separate categories and so on. This again is perfect application for Gaussian mixture modeling, but doesn't work with k-means because of how those things are stretched. But spectral clustering works great. And it's also interesting when you give it something that can't really be clustered, just to see what it does. And so both k-means and GMM do kind of similar things, spectral clustering too. But some of these other techniques maybe correctly cluster all those points into one and don't try to split it up. Okay, so that's it. So thanks for your attention. Hope you guys enjoyed the class. If you have some recommendations on ways to make it better for future semesters, please fill out the SEIs and let me know. I'm always looking for ways to improve the course. If you guys have questions about your final projects, please post them to the discussion boards. Hopefully those are going along well. So Tuesday night, midnight is when they're due. That's when the Kaggle competitions will close, so make sure you submit your Kaggle models. Make sure you mark in Kaggle the model you want to be scored, because sometimes, even though Kaggle is supposed to pick the best model for scoring, it doesn't always do that. The final scores on the private fold of the test set will be released once the competition closes, and those final scores are what your Kaggle rank is based on. Usually there's not a big difference between the private and public folds of Kaggle, but when you have a few groups that are pretty close, the order can sometimes change. The group that generalizes better rises to the top. So hopefully you guys are having fun with this, and any questions on anything, just come up and let me know. Sorry for going a little bit late today. Have a great weekend, and hope to see you guys around.